Okay, now the question that we're dealing with here has to deal with separation. And what I mean by the separation, think about, oh, I meant to be drawing there. Think about having a beaker or a glass even, and putting some oil and vinegar in there. They would actually separate and you'd have a distinct line difference. Well, organic compounds, all of them, will have a different solubility in those two layers. Sometimes they're going to be more soluble in the organic layer or the ether layer, and sometimes they're going to be more soluble in the water. And I would distinguish them this way. We're always going to have this ether, the organic layer or the ether layer is pretty much always on top because it's less dense than the water layer. Now, the two main examples we talk about early on in chemistry are carboxylic acids and amines. And I'm going to leave them kind of basic. So what I mean by that, we're going to put something pretty long in here, a pretty big organic compound, maybe as many as 6 carbons. Now the reason we're going that high, when we have that many carbons on a backbone, it actually guarantees that this part of the molecule only handles London dispersion forces or dispersion forces, and that would make this molecule with the H intact insoluble in water. And to a degree, same thing happens with the amine. If I take an amine and put it with, well, I'd need to put one more carbon here. This has only got 5 carbons. But anyway, this is a really big molecule. It's also going to be only soluble in the ether. So both these together would actually be in the ether portion. All right, what I can do to get them into the water portion is either add an H or remove an H. So carboxylic acids, because they are acids, very easily, and I'm going to rewrite this. I'm not going to write it as CH3, CH2, COO. I'm going to write R and then COOH, because the R is what this thing simplifies at. Well, if I take that carboxylic acid and put it into some water, or more importantly, if I put it into a base, I can neutralize this acid. And this becomes RCOO minus with some water. And the COO minus one would be more soluble in water. All right, so how do we know what's going on here? The neat thing is we can actually make a carboxylic acid favor the acidic side or the basic side by looking at the pKa. Because on a given acid, and most carboxylic acids have a pKa around 5, at the pH of 5, we would have about a 50-50 mixture, meaning that if you had this oil and water mixture, the acid would be split between the two, almost perfectly even. Well, the nice thing is about the pK and how it relates and how math works, if I go 2 units above this or 2 units below it, I can force everything to go to one side or the other. Meaning, if I go to a pH of 3, I will force this reaction to go to all the side that has all the protons on it. And our carboxylic acid would be in the ether section. But if I go to a pH of 7, 2 below it, I will totally deprotonate everything, put that charge on it, and now all of a sudden this will be in the water. Now, the amine does something very similar, but it almost looks like it's reversed the equation, because it turns out the amine gets charged. I don't want to write it like that. I want that R again. That amine gets charged when it's protonated. So we want to add an H to it or make it more acidic, and then it becomes RNH3 with positive on it. All right, so here, let's put a pKa of this amine, and it's more like a pKb because it's basic. And I'm going to put it around 12, which means at a pH of 12, we'd have equal amounts of this. But if I go to a pH of 14, more basic, I would favor the more basic side. And now it's actually in the ether. And if I go to a pH of, say, 10, to below this, we'll go to the more acidic form, and now all of a sudden it's in the water. So these two look opposite because it sees low pH or acidic pH, it's in water. Here, low pH was ether. The reason they're opposite is because the phase that's in the water is where our species is charged, and ether is non-charged. And that stays the same up here. Ether is non-charged, and the water is where it's charged. It just so happens that a base forms a positive cation when it gets neutralized, and an acid forms a negative anion when it gets charged. All right, but technically this is the thinking you want to use on any one of this type of problem to figure out where that solubility is balanced.